Now, an important thing to point out is that measure theory makes use of what we call the extended real number system. So measure theory makes use of the extended number system, the extended real number system, in which the symbols negative infinity and positive infinity are treated as literal numbers in particular, we're going to be interested in the non-negative subset of this extended number system. So we need to look at the rules of arithmetic. On the non-negative subset of the extended real number system, and that is the set from 0 to positive infinity inclusive. Again, we are considering the number or the symbol infinity as a literal number, and so when you see a closed bracket, it is implied that we're working within the extended real number system. Okay, so addition, we have that a plus infinity is equal to infinity plus a, which is infinity. And this is for any number a in the extended number system. Again, in this case, in the non-negative subset. Now, multiplication has two definitions. A times infinity is equal to infinity times a, which is infinity if a is strictly greater than 0, and 0 if a is equal to 0. So in particular, 0 times infinity is infinity times 0, which is 0. And for any other number in the extended real number system, in the non-negative subset, the product of infinity with that number is infinity. So, in other words, the only time that we have that a number times infinity is 0 is if that number is 0 itself. All right? Now, notice that the cancellation laws will hold with certain restrictions. For addition, we have that if a plus b is equal to a plus c, then this implies that b is equal to c only if the number a is strictly less than infinity. And for the product, we have that a times b, if a times b is equal to a times c, then this implies that b is equal to c only if a is strictly greater than 0 and strictly less than positive infinity. All right? Now, quickly, we'll talk about the topology on the extended real number system. And we call this the extended real line. And this is the order topology. Or the extended real line has the order topology. On this set from negative infinity to positive infinity inclusive. So the basic open sets, the basis elements, of the extended real line are, first of all, any open interval from A to B. But now this set can be considered to have a smallest element and a largest element. And so half open intervals of the form from negative infinity inclusive to A, and half open intervals of the form from A to positive infinity inclusive are also basis elements. So notice in particular that the extended real line is strictly finer than the real line. I'll state that. The symbol for the extended real line is just the closed interval from negative infinity to infinity. And again, when we see this, we assume that we have the order topology on the extended real number system. And so this this topology is strictly finer than the standard topology on the real line. All right. Okay, so a new definition. Let the set X together with the sigma algebra in X be a measurable space. Let the collection A sub I in the measurable set, or be a measurable set, for I in be a countable collection of measurable sets such that the intersection of A sub I and A sub j is empty. That is, given a countable collection of mutually disjoint measurable sets. Then a function phi from the sigma algebra into the non-negative subset of the extended real line is called countably additive, or sometimes we say sigma additive. If phi of the countable union of those subsets is the infinite sum of phi of those subsets. All right? So now we're ready to define a measure on a sigma algebra. So let X be a measurable set with the sigma algebra script M. Or a measurable space, rather. A countably additive function mu from the sigma algebra into the non-empty subset of the extended real line is a measure on the sigma algebra. So notice in particular that this is a function from the sigma algebra, not the underlying set, into the the non-negative subset of the extended real line. And the collection consisting of the set, the sigma algebra on that set, and the measure defined on the sigma algebra is called a measure space. Excuse me. So if we know the measure, then we know the sigma algebra because that is the domain of the function. And we also know the underlying set in the space because the largest set in the sigma algebra is the underlying set. And so, whereas logically it is this triple, the measure space is completely determined by the actual measure itself. All right? So now we're ready to look at the properties of a measure. So let mu be a measure on a sigma algebra. Script m. Then the measure of the empty set is 0. 2. The measure of a finite union of subsets is the finite sum. Finite sum of the measures of those sets. Now, neither one of these statements is as trivial as you might think, and you'll see that in the proof. And third, if A is a subset of B, well, we should state that if A and B are both measurable sets, and here we should also state that these are measurable sets. If A and B are measurable sets, then if A is a subset of B, then this implies that the measure of A is less than or equal to the measure of B. All right? So start with the first statement. Start with the proof. So let the set A be a measurable set. Let A sub 1 be the entire set A, and let A sub n be the empty set for every index n which is greater than 1. Now, without loss of generality, we may assume that the measure of the set A is strictly less than infinity. All right? So the measure is a countably additive function. And so that we have that the measure of the the countable union of subsets, A sub n, is the infinite sum of the measures of those sets. Now, every set A sub n in the collection, in the countable collection, is equal to the empty set except for the set A sub 1. And so this entire union is the set A sub 1. And on the right-hand side, we can write the measure of A sub 1 plus the sum from n equals 2 to infinity of the measure of the sets A sub n. So again, for these index values, n2 or greater, Each of these sets A sub n is the empty set, and so we have that the measure of the set A sub 1, which is equal to A, so we have the measure of A, plus 0 is equal to the measure of A, plus the sum from 2 to infinity, so an infinite sum of the measure of the empty set. And as we have assumed that the measure of A is strictly less than infinity, the cancellation law holds, and so we have that the sum from n equals 2 to infinity of the measure of the empty set is 0. Now this is an infinite sum of a constant term. The measure of the empty set is some number in the non-negative subset of the extended rule line. And so this, again, is an infinite sum of a constant term. And so we have that the product of the infinity with the measure of the empty set is 0. And as we know, there's only one number for which infinity times that number is 0, and that is the number 0 itself. And hence, the measure of infinity, or rather of the empty set, is 0. All right? Second statement. We're going to show that the measure of a finite union is the finite sum of the measures of the sets in the union. So let the collection A sub I for I in Z be a countable collection of measurable sets such that A sub I intersected with A sub j is empty. That is, it is a disjoint, a set of mutually disjoint measurable sets. And further, let's suppose that A sub I is equal to the empty set for every index value I greater than some n where n is a positive integer. Okay, so again, the measure is a countably additive function, and so the measure of the countable union of the sets is the infinite sum of the measures of those sets. Now, each of these sets, A sub I, are mutually disjoint, and for index values greater than n is the empty set. And so the union is a finite union, and that is the union from I equals 1 to some finite number n, which is a positive integer, of the sets A sub I. And we can rewrite this sum as well. Sum from I equals 1 to n of the measures of those sets, plus the sum for the index I equals n plus 1 to infinity of the measures of those sets. So we need to look at this term here. For these index values, we have for I equals n plus 1 to positive infinity of the measures of the sets A sub I. This is the infinite sum from I equals n plus 1 to infinity of the measure of the empty set, because each of these sets for these index values is the empty set. So, since the sum from I equals n plus 1 to positive infinity of the empty set, measure of the empty set, is still a infinite sum, and so of a constant term, and so this is infinity times the measure of the empty set, which we know to be 0, so we have infinity times 0, which is 0. And as that is true, we have that the measure of a finite union of measurable sets is the finite sum of the measures of those sets. All right? Third statement. Let A and B be measurable sets, and suppose that A is a subset of the set B. Then the set B can be expressed as the union of the set A with the complement of A in the set B. And to use the property of sigma additivity, we need to show that the sets A and its complement in B is empty, that they are disjoint sets, and that's very clearly intersection of A with its complement in a superset is empty, and so we can apply countable additivity, and so the measure of the set B is the measure of the union of the set A with its complement in the set B. And from the second statement we just proved, we know this to be the sum of the measures. And this is greater than or equal to the measure of A, because we are adding the measure of the complement of A and B. So this can be 0, in which case it's equal to the measure of A, or it can be a number greater than 0, in which case the measure of B is strictly greater than the measure of A. But it is true in either case that the measure of A is less than or equal to the measure of B.